introduction. It's my pleasure to have a talk about reservoir sediment management, especially for sediment drawdown flushing and also sediment replenishment below dams. Mainly, I will focus on the Japanese case study today. So today, mainly two topics about the sediment drawdown flushing. The previous talk is dam removal. Sediment flushing is more periodically, and we can select suitable timing and also to communicate with downstream impact. And sediment replenishment or some sediment augmentation is more like a small scale, but we can easily manage without large investment, for example, gates or other structures. So maybe my talks is how to select these methodology and maybe how to mixing and how to put a good solution for sediment management for long-term sustainability of reservoir. So first of all, I'd like some information about Japanese river. Yesterday, the Professor Takemon mentioned about the Tenryu River. He's our colleague. And we have conducted a downstream river environmental study in this river. But upstream is many hydropower dams, is many mountain area. So this is one of the typical Japanese power dams built in 1956, or already 60 years ago. 155 meter high, very tall dams. This dam is located here, and this is the original riverbed. Then we conducted almost annually a bathymetric survey. So based on those data, we can analyze how sediment coming in the reservoir and how deposit it and how making this kind of delta forming. And those data are very much beneficial to find future management strategy. In this reservoir is very large. So almost 85 or 90% of the sediment deposit. Only fine wash load is passing through the penstock and spillway gates. Coarse sediment deposit in the upstream and the middle reaches or sandy materials, and in deep areas or silt and clay materials. And as you know, this kind of large dams is like a kind of wave filter. I mean, the wave means the flat wave and the sediment wave. So flat is coming and the sediment is delivering to the reservoir. But flat already changing the wave, passing through, and almost the sediment is deposited here. So at a common understanding the dam construction or management drastically change the flow and sediment passage. And this kind of impact is going to downstream. And also in the reservoir itself is trapping sediment is losing the storage capacity for future functions. So now is we should solve this kind of situation is not only dam itself to maximize benefit, long-term beneficial for dam reservoir or function, and also downstream river restoration issues. So in Japan is many issues downstream impact. For example, this kind of too much vegetation is occurred in downstream rivers. So this kind of vegetation is not good for safely passing of flat flow. So how to do that? And also this kind of too much armoring also occurred. Is also environmental issues is not so good for. And also up to the river mouth area. This is the river mouth of Tenryu. In the 60 years ago is we have sandy, very beautiful beaches, but now is not only a large dam impact. Is in the high economic growth, we Japanese a community taking so much sand, gravel from the river channel for construction work. So this kind of two impact is already occurred. But now is the Japanese government is almost prohibited to take directly to taking the sediment from the river channel. But in the future is this kind of upstream sediment deposit will have a long-term impact from now. So we should consider also the reservoir issues. So our challenge is how to consider the upstream issues and reservoir issues, channel and river course, and how to integrate it, those management, not only separated, how to communicate and how to share the information, and we should or more wider scope of our strategy. This is integrated management of sediment, river basin scale. So our approach in Japan is Japanese government is conducted some step by step is requesting the all dam owners from the 1985. Currently, the reservoir keeping the storage volume for sedimentation is almost 100 years. And also we have the guideline to take data almost annually, how the progressing the reservoir sedimentation like this. Not only the reservoir area, upstream is sometimes is a gradation occurred. So this kind of gradation is causing some artificial flood in the upstream area. So this is also key for local community in the upstream area. So government is taking or requesting the data, and those data can be utilized for making some strategy. Now is almost 3,000 dams in Japan, more 15 meter high, and almost 1,000, one third of dams is collecting data reported to the Japanese government. And based on those data, we can categorize as how now the current stage of sedimentation. This is storage loss already field of sediment. How much percentage the field of sediment? And okay. So this is like a specific sediment yield, like a unit area, how much sediment is delivering from each area. So we can understand that we are now in Takayama is belong to the tube area. So tube area is high mountains, so very high specific sediment rate, and already there's so many sediment deposit in the reservoir area. And more close up this area, Takayama city is here, and maybe tomorrow we will go to the Hodaka area, mountain area, and high sediment rate is expected. And Kurobe River is like a Saturday. We have the post-study tour to that area, also very high, this kind of sediment rate. And in case of Kurobe River is this kind of many steep valley and devastated area. From there is too much sediment coming downstream. And to look for the reservoir sedimentation issues, this is almost 1,000 dams in Japan is plotted here. So this is the reservoir age from the beginning. And some marks show is operation body. So in the past is mainly hydropower dams. After the World War II is multi-purpose means flood control included. Those dams belong to the central government and the local government. And those dams is, of course, need to keep the good storage for future generation is very much important. But gradually increasing the sediment deposit. So how to deal with this for future work? And the important point is, if possible, we should release or to minimize the sediment deposition in the reservoir. That is very much beneficial for reservoir and downstream. That kind of strategy is very much important. So not only the quantity, quality issue is also important. We have conducted several points of bore coring, and we can take coarse material and sand material, fine materials from each area, and also some organic material, how much percentage contained. Because if we consider to release those sediments, it's not only sediment side, this kind of material is also very much important to assess the environmental impacts. So next question is, if we consider the reservoir itself and the downstream point, how to finally define the suitable or appropriate volume and size, for example, quality of sediment. So if we consider the volume, we will consider the reservoir point of view, how much sediment should be taken out for long-term like sustainability, and how much sediment volume is needed from downstream like a necessity point of. This kind of like a discussion is needed. And regarding the methodology, Japan, we are trying to develop many methodology like this, is reducing the upstream or trapping issues and bypassing issues. Today I have almost no time to bypassing issue, but we are closely collaborate with Swiss people how to bypass the sediment directly to the reservoir. And also the taking sediment can be utilized for downstream input and drawdown flushing. And also conventional excavation, dredging is many methodology we have. So those are like outcomes should be published and also shared worldwide. This is one example is Professor Matt Kondorf is he collected some Japanese case study in this paper. So please share this one. And in this paper is some methodology listed up like this: upstream reduce sediment yield, and minimize sediment deposition means the passing or sluicing methodology, and recovering volume is excavation or drawdown flushing like this. And Japanese cases, I already mentioned there was 1,000 case study. So we can plot it in this kind of chart. At the horizontal data parameter is like a capacity to mean annual runoff. So that this is like how many times is water will be turned over in the reservoir annually. And the vertical parameter is like how much volume sediment coming to the annually. So we can say that this is a reservoir life. How many years to be needed to fill up. So we can categorize many dams like this. Mainly here is like a large volume reservoir. So at the moment, no critical issues for sediment releasing for reservoir sustainability. But this dam is too much faster coming sediment. So we need some strategies, drawdown, excavation, or sometimes bypassing issues needed for reservoir operation. So maybe we can categorize 4 groups. Then based on these groups, we can assess each methodology and which timing is suitable to start. That is next question. So those data also included the other countries' data. So George Hernandez is also mixing the other data in the worldwide. This chart is very much useful to find or feasibility study the existing structures. So now this kind of chart is updating by the Technical Committee of Reservoir Sedimentation, ICOR, International Commission of Large Dams. So I'd like to go to the flushing case study in Japan. This is a Kurobe River case study. The drawdown flushing is drawdown means usually keeping the water level and periodically draw down and sediment erosion and passing through the bottom outlet. And after some duration, we will refill again. So worldwide, I guess there's many this kind of similar case study. In Japan, these 2 dams is located in Kurobe River. And other Swiss and France is India, many China, many cases also available here. And one other case study in the Rhone River from the Swiss to France is 2 dams or 3 dams is drawdown flushing, a kind of cascade system. 2 dams. Drawdown a concept is like this. So almost the same concept we are doing in Kurobe River. Kurobe River is a very steep river, almost less than 100 kilometers total length. And the upstream is the highest dam in Japan. Is Kurobe River is a very famous arch dam in Japan. But the downstream Cascade Dam is limited storage volume and receiving so much sediment. So originally those dams have designing the bottom outlet for drawdown sediment passing. So drawdown concept is like this. Two dams is like almost same time. It start to draw down, and sediment like erosion passing, and refill again. This kind of like scheme diagram. And the important question is when we will do this operation. So finally, we are concluded the rainy season, June or July. Here now is September is typhoon season. Typhoon is sometimes coming, but sometimes not coming, and very short period and very difficult to expect the rainfall rate. But June and July is more sometimes easily to like predict. And this area is a mountain area. We have so much snowfall, so base flow is a bit higher than other seasons. So this kind of very much advantage point to minimize impact for downstream. So, but from the beginning, there is some historical background. Is Dashidaira Dam is 1955 built, and the first flushing is 1991. But at the time, is some this operation is conducted in the winter time, December. So low flow and too much concentrated sediment is discharged to downstream. It's a severe water quality problems occurred. So after that is tentatively stopped and conducted the sediment flushing evaluation committee how to solve these issues. But 1995 is we have the big flood at the time. So we have no time to stop, or we should restart. Then after that is 3 years restarting period. And after that, 1998 is a general flushing operation started. And after that, 2001, Unazuki Dam, another dam is built. So currently, 2 dams is under operation of this kind of cascade sediment drawdown flushing. So maybe this kind of a situation you can find if you visit this Saturday trip in Kuroberiba. So, okay, this is a video, the drawdown flushing of Dashidaira Dam, upstream dams. This dam belongs to the Kansai Power Company, and this dam is belong to the Ministry of Land Infrastructure, Transport, Tourism, means the Japanese government. These 2 dams is operated drawdown flushing almost the same time. So these 2 dams is periodically almost annual sediment flushing. So deposited sediment almost stable at the moment. I mean, the annually coming sediment can be flushed out in the next year. So no too much progress. And this one. So this is a current deposition profile. So yes, this is upstream of Unazuki Dam during the drawdown. Then before starting, we have this kind of physical modeling, which area to this kind of outlet should be designed to consider the flushing channel formulation. And also the long-term use, we should consider the big global impact for the channel. So too much aggradation, erosion occurred in the channel itself. So upstream area covered by the stainless steel plate, and downstream is conventional steel plate, and downstream area is very hard strength of natural stones, for example. This kind of mixture is used. This is inside of the outlet of Unazuki Dam. You can see that this kind of gravels are passing from the bottom outlet. And some discussion over or challenges of sediment flushing is flushing efficiency, or how much sediment can be flushed out and how effectively flush out in the total reservoir area. And another one is how to consider minimize environmental impacts. So you can find that this is a flushing channel formed during the drawdown in the Dashidaira reservoir. We can understand this kind of channel formulation in the longitudinal degradation and also lateral side bank erosion. So this is one example. 2006 is a drawdown operation, and also some sediment concentration is released to downstream. And this is a record of how much water used and how much sediment is flushed out, and at the time how much sediment concentration occurred like this. So based on those data, first we can understand that how much average concentrate of sediment is released using the water. You can see that compared to the other case study, that we can almost summarize the 2% or 5% of concentration is sediment released during this kind of drawdown operation. Using those data, we can like an empirical formula like this. If we can estimate the concentration of sediment and the total usage water annually, because like too much longer drawdown is not good for dam operation itself. For example, power generation cannot be done. So how much water can be utilized? These two parameters is very much key for assess the like feasibility of drawdown flushing. So using those data is if we consider the beta is like how much percent of water it can be used, and FE is like flushing efficiency. If we consider the 2%, and this one is 10% of total water can be utilized for annual water for sediment passage. Then again back this the chart. Maybe this is a kind of like a borderline to be like effectively utilized as drawdown flushing. So worldwide example is located here. Our Kurobe River case is also listed here. This one is like a relatively smaller size or some middle size, and it's a good water can be passing sediment. Those dams is like feasible to this kind of drawdown flushing. But the middle size, more larger volume of reservoir or more larger one is maybe you can easily understand to draw down and to recover like periodically. This one is should be considered another solutions. So we conducted several like field survey. This is one 3D laser scanning in the like this kind of like side bank erosion during the drawdown. And also those data we can assess the like channel formulation compared to the like previous study. And also we conducted also the numerical like models using the 3D SIM2. Our PhD student is doing the these two dams flushing channel formulation. Like this. And also this is Dashidara Dam. And the interesting point is during the drawdown, in case of Dashidara Dam, Unazuki Dam is during the drawdown this kind of like a flushing channel formulation, but some timing is like a channel is like a kind of migrated in the reservoir. This kind of like data is very much like beneficial. How much duration or how much timing we are keeping the drawdown to enough sediment erosion from the reservoir area. And also the downstream impact we are conducted in the downstream area, because this dam is anyway steep and narrow and very close to the river mouth. So we conducted environmental monitoring in the reservoir area and also the river area and the river mouth and the coastal area as well. So main point is like dissolved oxygen and the sediment concentration at the real-time data real-time basis, and also the before and after the how those sediment is deposited and how changing the riverbed size and the aquatic species and also the vegetation issues. Those data is like very much important for long-term like assessment. And discussion about environmental issues is water quality and the deposition in the riverbed and how to minimize what kind of methodology we can do. So important point is, for example, the too much deposited occur downstream. Maybe we can like clean using the like more clear water afterward. This kind of like rinsing flow operation also we are starting. And also, of course, not only the like adverse point, like a positive point, it should be considered in the downstream issues. So this is one example is during the drawdown is sometimes a high concentration flow is released, and if the like critical cases too much quickly drop down of the dissolved oxygen occur. This is maybe sometimes a fish kill downstream. So this is very much careful issues. But in case of Cloveriba is nowadays almost no like a drop down of dissolved oxygen, but still high concentration occurred. So we are carefully monitoring those data and to impact downstream. Thank you. This is a typical fish in Japan. Is yesterday Professor Takemo mentioned this is a sweet fish. This is like very much common in the Japanese river. Also, fishermen is take care. This one is how impact. But unfortunately, this fish is very much like sensitive to this kind of turbidity. So we are conducted like a field survey. This one. Based on this concentration of sediment, is we can use this kind of like stress index. Is this is calculated by the concentration and duration. It is like accumulated impact. So based on the data, we can like draw the which year which flushing is sometimes critical or not safe or not. This kind of data is very much useful for assessment. Anyway, is high concentration is very much efficiency, but too much, sometimes too much like stress. But the low concentration is maybe we need too much water. So how to balancing these issues is very much important. And the downstream impact is like we have conducted the riverbed change in the step by step, and also the grain size distribution also monitored. And started this kind of operation is slightly recovering to the original state. And also the coastal issues, Kurobe River is coastal is historically too much eroded. And nowadays is coastal line is slightly recovering this kind of sediment input from the river mouth. This is a very much positive point. So many lessons learned from this Kurobe River. And so we are like almost like finalizing our methodology. And now is staging to monitoring the long-term benefits. But to minimize like impact, we already started rinsing discharge just after filling the reservoir water. Overflow, slightly low concentration flow will be additionally releasing to the downstream to like flush out too much deposited area. That is beneficial for next time. And also we created some like evacuation channels at the side of the channels. Because during the high concentration passing in the mainstream, sometimes the fish can be like going inside and to keeping there, just passing after, then they recovering to the mainstream. This kind of like evacuation channels is sometimes important to mitigate too much stress for the fish. So, okay, so 5 minutes? 5 minutes? Okay. 3 minutes, okay. So finally, I just talk about like a sediment replenishment issues. This is like a main point today about the drawdown flushing. And also we had conducted many sediment like check dams and mechanically or excavation and to input to downstream. So this methodology is, I understand, very much common worldwide. And we are now staging to how to categorize or how update this methodology. So how to input or how to put the sediment in the river channels. This is an example in the Japan, and this is an example in the Trinity River in the state of California, US. And in Japan, we have more commonly used, more than 20 dams is doing this kind of sediment input. So now our challenge is how much sediment we can take, because this kind of taking and tracking to downstream is sometimes tough work and very much need cost. So how much volume of sediment compared to the annual sediment volume is a challenging issues. 1 to 10 is 10% of annual sediment deposition. This is 1%. Now is our example is up to 10% of sediment now is excavated and to input to downstream. And another issue is how grain size we will design the fine material, mainly coarse materials, because of these coarse materials coming from the upstream sediment trapping dams, so more easily to take or excavate. And finally, we should consider that those benefits. This is provided by Professor Takemon. Flow regime and sediment supply should be considered geomorphic responses, but we should carefully communicate with the habitat and also biodiversity and the material cycle issues. This kind of closely communicate is needed to define the suitable volume of sediment. So, okay, maybe limited time. So this is a case study in the Nunome River in Japan. We put sediment like this from tracking from the upstream. And during the flow discharge from the upstream dams, this kind of deposit sediment is naturally eroded and to input to downstream. So how to monitor the benefit? This is one example. This deposit sediment will be captured, for example, reservoir plankton from the upstream reservoir. So this kind of newly deposited material will be filtering the upstream water and capture the plankton from the reservoir to cleaning to the downstream. This is one benefit. And also the creating the new habitat for more diverse benthic macroinvertebrate also created downstream area. And this data is we can share with other project. This is one example in Trinity River, US. So our PhD student is visited Trinity River and to conduct this kind of field survey. So how to assess that those newly deposited sediment is changing the, for example, thermal condition and also the filtering condition. Or the data is very much positive to create a very diverse thermal condition downstream, and also the filtering effect is very much positive. So anyway, this kind of newly sediment input is very, very much beneficial for downstream. So, okay, this is a final slide. At the end, we have many dams anyway. Then we categorize the normal impoundment reservoir, sediment replenishment, sluicing, and sometimes it's partially drawdown or sediment bypass. And sometimes we have dry dams is usually only for flood control, usually completely drawdown, and decommissioning. These cases, how much sediment is passing through the downstream, and how much size of sediment passing, and maybe how to select the suitable options. If we are now at a stage of a normal one, maybe some investment is more chance to passing through the sediment to downstream. This kind of discussion is needed. Thank you very much.
All right. Thank you. We'll work from over there. Thanos?
So I got a question actually for both of you. John, you mentioned that, but system resilience, and you gave some good examples. And you've shown actually two contrasting videos. One is the Condit Dam, and then the the Marmot Dam. Is the Condit Dam a bad example for removal when you've shown there a lot of removal, a lot of mass failure actually taking place? Do you qualify that as a bad removal example?
No, I don't think I'd classify that as a bad example at all. It was just an alternative example, a way of that was one way of rapidly evacuating the sediment out of the reservoir. What actually happened at Condit Dam was all those landslides liquefied into a hyper-concentrated flow that flushed down the system. It deposited a relatively modest amount of sediment through the system, and the fines and the sand separated. The fines kept on going all the way down to the Columbia River. The Columbia River was about 5 kilometers downstream. The fines went on into the Columbia and washed through. The sand draped the system, filled a lot of the pools, and right at the confluence with the Columbia, there's a very deep pool. So that pool filled in. But through the bedrock reach upstream, the system it eroded back down to the level of the riffles within a matter of weeks. So this is where morphology of the river system comes into play a bit. So again, you had a bedrock reach downstream of the dam, so it was able to pass most of the sediment through that bedrock reach. It filled the pool. So that pool is still feeling the effect of that removal several years later, but that pool was also somewhat artificial, partly a response to the sediment starvation from the establishment of the dam. So I don't think I'd say that was an example of a bad removal. It was an alternative removal.
What about, the bank stability? I mean, did the channel kept widening or?
It widened for a little bit more. I guess in that particular example, there were a number of homeowners that lived around the reservoir. That was a nice lake, a recreational lake for them. From their perspective, maybe it was a bad removal simply because the lake went away and the water wells in the area dropped down, so they lost their water. So from their perspective, yeah, it was perhaps a bad removal. But that reservoir was revegetated fairly quickly afterwards, and there's a lot of bedrock in there. So it widened quickly and then stabilized fairly quickly.
Okay. So a very quick question, actually, for both of you. Do you have any methane information about methane storage behind small or medium-sized dams? And
I'm not aware of any particular studies of that. I don't know if Dr. Sun is.
What kind of study?
methane.
Uh-huh.
Do you have any information about methane storage behind, small or intermediate-sized dams?
Not so much information for us.
Yeah, you've shown, some measurements about dissolved oxygen, and I was trying to see if you can make some inferences based on that.
Yeah, one comment I'll make, I don't know if it was methane, but there was a large amount of organic material stored behind the Condit Dam. And as that flush came down the system, it released a lot of that organic material. You could smell it as it came down the river system. And our colleagues who were down at the mouth of the channel said that as that hyper-concentrated flow came through, they could see the fish jumping up and gasping for air. So the dissolved oxygen content dropped considerably as that hyper-concentrated flow came through, carrying a lot of the organic material.
In case of Crow River, is first experience flow release is too much water quality change occurred. So firstly, we understand that is coming from the organic materials. But after that, carefully designed, we also changed the ideas of more chemical issues. Also the ion, ion or contents in the deposit materials is also very keen for the change of quickly a drop down of the dissolved oxygen. So those data is we are so much accumulated now.
Let's go over to Helmut, and then we'll move back. So.
Helmut Habersack, Austria, Vienna. Thank you very much for the both very interesting talks. In Austria, we have a lot of discussions about this, not about dam removal. It's not a discussion point yet, I would say. But the general problem of reservoir sedimentation and the consequences downstream is an issue, and I have a question for both of you. we try to discuss what is the best option as well, to flush, for example, or to have a bypass system. There's also discussions with the turbine construction company, Andritz, at the moment, to design new types of turbines to get to turbine more water without the abrasion consequences and things like that. I was just wondering, we came to the conclusion recently that maybe turbidity currents would be one option without having to drop down to lower the water level. But as we know, we need a temperature difference between the ingoing reservoir water and the reservoir water. And we have to have a nice bottom outlet. We have to have not a mixing process in the reservoir. But if it would work, if we would have the preconditions, and we don't have it in many cases, but if it would work, for us at least in Austria, it would be the best option because we don't lose the operation. We keep the storage, and what comes in goes out. So we have no environmental problems because no one could complain for the fish that because we don't change the system, if you wish. We just open the bottom outlet and let the water go through within the density current. So I was just wondering if in Japan or in the US you have some examples on turbidity currents and what are the restrictions, and if this is also an additional option for certain situations.
Regarding in the Japanese case studies, we are usually bottom outlet, and if we can open that bottom outlet in good timing for turbidity current venting, we can use. But in Japan, is like a flat duration is very short, and reservoir size is not so large. So my understanding, they're like a stable density current cannot formulate all times. So this kind of if downstream river is need more coarse sediment, that's why we are taking capturing the upstream sediment and putting downstream. But this kind of operation is of course important because if we not this kind of operation, fine sediment is just accumulating in the reservoir, and the future, if the bottom of sediment is going up, then in the near future, with this kind of sediment will be resuspended and discharged downstream. That is the only timing. So we should start now. Thank you.
I saw Kimberly next, so getting over to her. Yeah.
I have a question for John. I'm wondering, you mentioned some details about how you monitored where the sediment was going based on size, but I'm wondering if you looked to see, I didn't see how you did that. Did you take cores of the bed so therefore could find out if you saw anything about fines fouling and looked for that? If you did on the short term or long term, if you saw any effect after the dam removal of fines fouling of the bed?
Now, are you talking about the marmot, that example, or just in general?
Marmot in particular, but also in general. The marmot had sand and gravel, if I remember correctly, right, but maybe a little bit of mud to foul it. Yeah. Right.
There was a little bit of mud at Marmot. It was mostly capping the top of the reservoir. And so actually some of the very first sediment that we caught in this, monitoring the suspended sediment that came down and the turbidity levels, that was the really fine stuff right at the top. Once it started to incise into the sand and gravel below, there really wasn't all that much mud in there. It was mostly just the sand and gravel. All we can say with regard, we know that the gravel deposited in that first couple kilometers. We've got a number of surveys to look at it. We were monitoring the sediment coming out of the gorge, at the bottom end of the gorge. A little bit of gravel came out through the gorge. It was almost all the sand that came out from the gorge. One of the challenges is we don't really know where all that sand went. You've still got, from the bottom of that gorge to the Columbia River was still something on the order of about 40 kilometers downstream. And the Sandy River is a very dynamic river system. And so most of that sand got spread out along that lower 40 kilometers. And it's really hard for us, try as we might, we were not able to go to any one spot in that 40-kilometer reach and say, this is the sand that came from that removal. So we really don't know exactly where all that sand ended up. The assumption is it spread fairly thinly across the system. In the case of the Elwha Dam, getting to your point on the fines, they did see some of the first sediment that came through the system was fairly fine grained. It was muddy and it draped the system. From a geomorphic point of view, it didn't really do that much. It didn't have much geomorphic effect. But from an ecological point of view, it can have a pretty big effect. They did see that a number of the fines infiltrated into the gravels. But all that happened before the big wave of the big flush of sediment came down through the system. So the fines themselves, from a geomorphic point of view, didn't have a lot of impact. But from an ecological point of view, they can have a very big impact if they start infiltrating into the gravels. Yeah.
So that's interesting for us because it coincides with what we saw experimentally, that the fines can have no effect on the slope, but can infiltrate quite a bit. And I'm also curious, do you monitor that in the long run after the dam removal? Because you talked about how the slope recovered fairly quickly, and you showed monitoring after it recovered, but do you also keep on watching somehow by coring or some other method?
At Marmot Dam, we actually dig pits to look at the grain size, what grain sizes were in the subsurface. And at Marmot, we essentially found that it was just that it was mostly the gravels. It was rather interesting in that the grain size composition at the surface and in the subsurface before the Marmot Dam removal in the gravel bars and post-removal after a couple of months were virtually identical. So that was, even though you released all the sand with it, the sand didn't accumulate in those gravel bars. It kept flushing. So we do have some data that shows that. At Marmot, it's just insignificant amount of fines. But at Elwha, there was a fair number of fines that infiltrated. Another dam removal in Montana, the Milltown Dam removal, our colleague Andrew Wilcox monitored some grain sizes about 15 or 20 kilometers downstream, and there they also found that some of the fines had infiltrated into the gravel. So they do have an ecological effect, that's for sure.
Let's have Tim Randall there at the end.
Well, thank you for those really good talks. So Tim Randall, U.S. Bureau of Reclamation. I really like having these together because I think the dam removal case shows sort of the extreme situation for reservoir sediment management. If you are releasing sediment from the reservoir for sustainability, usually far less than trying to empty out the reservoir of sediment. So we're, I think, learning a lot from that. In the case for the dam removal, I think it's helpful to look at the sediment volume relative to the mean annual sediment load of the river as a way of sort of scaling this in. I haven't really come up with any great solution, but trying to look at maybe the reservoir width relative to the river channel width as a way of getting an idea of how much sediment might actually come out of a reservoir. So if you imagine a narrow reservoir, you might expect all of it to come out. In a really wide reservoir, it might be harder to get a lot of that out. And I think that has implications for both reservoir sediment management as well as dam removal. And that might help reduce some of the scatter in the plots you're seeing. Also on both Marmot and I think the Elwha dams, we've seen some degradation below the dam, or local scour, if you will. And in the case of Marmot, you had the flat spot in the profile that seems to have filled in and may be permanent. I don't know if that will stay permanent, but with the hydraulic head drop over the dam, you can imagine how that's kind of scoured out and flattened. And below Elwha Dam and Glines Canyon Dam, we had some of the flattest slopes on the river, and I think that's more than just coincidental. I think it's having a century of water going over those dams has degraded those slopes, and I think they're permanently degraded in both the Elwha Dam cases, Elwha and Glines Canyon, and maybe that can explain where some of the gravel is going to sort of permanently reside.
In the case of the Marmot, what's been interesting, and this is where I said that unfortunately there are not, we lack long-term studies of longer-term response. But interestingly at the Marmot, we had that very flat profile right below the dam, and then it filled in with this wedge of sediment. And that wedge of sediment is beginning, the profile on that is beginning to flatten a little bit. I mean, it's not flattening back down to the profile that was pre-removal, but I was surprised to see that it was beginning to start to flatten out, and suggests to me that there's more kind of a broader morphological effect going on. It's not just that the gravel parked there, but that that narrow valley right through there, it's bedrock confined, has some influence. So I'm not convinced entirely that that pre-removal flat slope was only due to sediment starvation and water coming over the dam. But that is where most of the gravel parked. I was going to make another comment in the first part. Your comment about the volume of sediment versus the background flux, which is what I was trying to get at in that one plot, what I called the V-star, the one with the red triangles. And the idea there was can you anticipate maybe in advance, if you know the volume of sediment that's in the reservoir, and you have some estimate of what's kind of the mean annual sediment flux at that site, that ratio might give you some qualitative insight as to how long it might take for that downstream river system to respond and get back to some sort of state of at least quasi-equilibrium. You know, if you've got a volume that's, say, 100 times more than the typical background flux, you might anticipate it's going to take some time for that river to kind of clean that up. But if that ratio is maybe 10, the river system might get back to some sort of state of stability in a relatively quick amount of time. And one of the biggest fears, you know, these managers, their big fear is, you know, releasing large amounts of sediment to the downstream river system. What's going to happen? And I think what we've seen, at least from that limited database of studies we have, is that those fears are not quite, you know, they shouldn't be quite as fearful. That these systems are somewhat resilient and they tend to respond and they clean themselves up and they tend to stabilize, at least within some range of variability, relatively quickly. Whereas back in around 2000, it was you know, Jim Pizzuto wrote a paper and suggested it could take decades for these systems to really get back to some state of stability. And we're seeing it doesn't really take decades right now. At least in these removals that we've seen so far, it's maybe a few years.
So the powers that be did say, let's keep the questions going because, hey, that's why we're here. Bill has been eagerly awaiting a question since the beginning.
Well, yeah, this is Bill Dietrich, Berkeley. Dam removal, flushing experiments, replenishment and recruitment are experiments. You can do calculations. People have done calculations on what might happen, and then you can actually test that. And I'm curious, you mentioned briefly in your talk, but I think you were running out of time as we didn't get to hear as much as I'd like to have heard. And Don, you didn't mention at all the role. And so tell us in your review, in your Powell committee, what has been the role of fairly substantial development in numerical modeling that you can run the model before you take the dam down and see how it's performed. That was done on the Marmot Dam. Are the models working? What do we not know? Where are we with that? Because it seems like it's a very important tool that's been advanced that should be used as part of making the decision instead of worrying about whether it's decades or weeks or months. You can do a calculation and then test it. So where are we with that?
Well, sure. I mean, there's been a lot of advances in say, the past couple decades or so with numerical modeling of removals. And as you mentioned, in the case of Marmot, I avoided that topic simply in the interest of time. But there was a model that had been run at Marmot. It predicted what the impact would be. And generally, overall, that model did pretty good. It was a fairly simplistic model, but it did a pretty good job. It generally predicted where downstream the gravels were going to accumulate, kind of where the sand was going to end up. The model, where the gravels ended up pretty much is where the model said. Like I said, it was a little hard to test the model predictions of where the sand ended up because we haven't really been able to tell exactly where the sand has ended up. In the reservoir, it appeared to us as if the model underpredicted the rate of evacuation, that the reservoir evacuated the sediment more rapidly than the model predicted. But otherwise, that particular model, this is the DREAM model by Yantai Sui, did a pretty good job. It's the only case I'm aware of right now where that level of detailed model prediction had been done. We are. I agree. I mean, these are one-off experiments. It's too bad we can't rerun them. But yeah,
And downstream, it was difficult as well because the models were not at that time taking into account how the transport capacity would really increase when you change the grain size like we did. Because we had high concentrations and the river proved to be very resilient and very good at transporting that sediment all the way to the ocean. And I think the models had a hard time predicting that part of it. I think they could do better today than we had 15 years ago. But well, we had a laboratory model of the reservoir. It was just the coarse fractions only. It was none of the fines. There were some scaling issues, but even so, I think qualitatively, the laboratory model that Chris Bromley did, Colin's student, did a very fine job of predicting qualitatively how that would respond. And it also helped us inform us that we needed to have a pilot channel down the center of the delta. Otherwise, we would have had, I think, incision along the margins and left a huge portion of the delta uneroded.
I'll try to channel Gordon here a little bit. There was also a physical model that had been done for the Marmot Dam. And on the basis of that physical model and various scenarios, you notice that in the little video I showed that the notch was cut on the very far side of the dam as opposed to, say, in the middle. And that was done on the basis of results of the physical model that Gordon had been involved in. Because there were bedrock confinements upstream, and the fear was that, as the Nick Point migrated upstream, it might get hung up on a bedrock ledge. And their physical model showed that if they put the notch on that one side, it would minimize the probability of the Nick Point getting hung up on a bedrock ledge. So that's why it was. So that physical model helped guide the actual implementation of the removal.
Tetsuya? Yeah.
Okay. Yeah, regarding how to utilize the modeling, we are using the 1D for the implementation basis because during the drawdown flushing, in the dam office is inviting the many consultant firm, and they are using the updated data and 1D. And the important point is when we can stop the drawdown. Then they stop or close the gate and they start to refill. Because firstly, the drawdown is too much sediment is effectively eroded, but in some duration is some efficiency will slightly decreasing. So just clear water passing is not good for power generation. So they are very much keen about which timing we can close the gates. And they are doing this kind of 1D model on site. Those data can be feedback for operation optimization. And today I show you the 3D. That is not a real-time basis. So we are studying how to increase the efficiency using the combination of dams, for example. If upstream dams can be additional clear water can be supplied to downstream drawdown timing. So how to change the flushing channel formation and change the concentration or efficiency considering environmental point of view and sediment flushing issues. So that's kind of several scenarios we are testing using this model. So maybe we can use both. Thank you.
So last one, I'd like someone from the back of the room if there are questions, just because everything has been in front. John, please.
Whether you've taken advantage of the flushing operations in order to undertake two additional things. One of them is in order to determine what happens during a big flood. Because here we have a situation where, and this has been done in a few places, where you know in advance at what time you're going to have approximately what discharge, for how long a period of time. And I know that, for instance, in the Arc and Morin in France and some other places, this is, they're taking advantage of that for two different purposes. One of them is related to what kind of bed forms are there and how they change and how they migrate and what is stable at what conditions. And the second is sediment discharge, how much is moving where and how. And it seems that at least in sediment flushing operations, there is an additional advantage that I'm not aware whether it has been done in Japan or elsewhere, in that if you undertake a resurvey of the reservoir, and if you know what material therefore has at least been evacuated, there we have an exceptional condition where, in addition to modeling, there's also, these are wonderful tests, and governments spend a lot of money on, or private companies. So has any of that been done in Japan, or if others know elsewhere? Thank you.
Important point is like a kind of triggering is when we will start, for example, drawdown. We initially fixed at the season at the beginning, 2 months. I already mentioned June and July is a good season for drawdown flushing. But when we will start the drawdown, that will depend on the rainfall events. So our base flow is already high, but the additional rainfall, we will create the additional water runoff. So that is more like reducing the impact for downstream. So that's kind of like a meteorological rainfall prediction we are doing it so much intensively in that local area, the Kurobe area, because very much like a complicated mountain area. It's very much tough work, but we can improving that kind of prediction work. Yes.
All right, so it is 12:40. Let's thank our speakers again. And I assume it's lunchtime.